Dear student, this is a new chapter on heat exchangers, and in this video I'm going to introduce you to the concept of heat exchangers, their applications and the classification. Heat exchangers are devices which are used to transfer energy from one fluid to another fluid when there is a temperature difference between the two with minimum investment and maximum energy transfer. We see many applications of heat exchangers in daily life. Example of a car radiator where the engine heat is applied to water, and water which gets heated up will be further cooled by atmospheric air. So water and air are two different fluids between which the heat exchange takes place. So car radiator can be an example of heat exchanger. Similarly, in a refrigerator we normally see two different heat exchangers. One is evaporator and the other one is condenser. The evaporator takes away the heat from the air within the refrigerated space, and there will be an exchange of heat between the inside air and the refrigerant. Whereas in condenser, there is an exchange of heat from the hot refrigerant to the atmospheric air, and sometimes you can use the tubes with fins to enhance the rate of heat transfers. And in case of a power plant, we may see the use of evaporators and also steam condensers also, because most of the times water will be recirculated back into the cycle. In such cases, this steam condensing is very important, and steam condenser is another example of heat exchanger. Heat exchangers are available in various sizes, types, configurations, and flow arrangements, and these are used for different applications. Based on this, we have different classifications. Main classifications among them are, according to the flow arrangement, we have three types: parallel flow, counter flow, and cross flow. According to constructional details, tubular heat exchangers, shell and tube heat exchangers, and also plate type heat exchangers. According to heat transfer process, we have direct contact type, wherein there will be a direct contact between the two different fluids through which heat exchange takes place, and recuperators, where there is no direct contact between the two fluids. They are also called as indirect contact type. And we have regenerators or storage type heat exchangers. And also, according to physical states of fluids, we have condenser and evaporator, where there will be change of phase of a fluid. Parallel flow heat exchanger is one of the heat exchanger based on flow arrangement, and in this case both hot and cold fluids enter at the same end of the heat exchanger, and they flow through in the same direction, leave at the opposite end. And if you observe the sketch carefully, the central pipe through which the hot fluid is flowing, the inlet temperature of that hot fluid is Th1 and the outlet temperature is Th2. And similarly, cold fluid which is flowing inside the annular space between the two pipes, central pipe and the external pipe. So the temperature, inlet temperature of which is Tc1 and the outlet temperature of which is Tc2, is flowing together with the same direction as that of the hot fluid. Since the direction of both the fluids is the same, we can call it as parallel flow heat exchanger. And to the right side we have temperature variation of hot and cold fluids as it flows along its length. It's been given, and you can see the temperature of the hot fluid decreases along the flow direction, whereas temperature of the cold fluid increases in the direction of flow. And L is the total length of the heat exchange which is in contact, that is hot and cold fluids are in contact. These are also called as co-current heat exchangers, because both the flow currents are in the same direction. It's also called as co-current heat exchanger. Counter flow heat exchangers are those devices in which the flow of fluids, that is hot and cold fluids, are in the opposite direction. They enter the heat exchanger in the opposite direction, and also they leave in the opposite direction. And if you can just check now in the sketch that hot fluid is flowing through the central pipe, and cold fluid is flowing inside the annular space between the two pipes, but in the opposite direction, because of which you can see the variation in temperature profile, wherein the temperature of the hot fluid, yes, it is decreasing from the inlet to its outlet, but and also temperature of the cold fluid increases from its inlet to the outlet, but the exit of cold fluid is almost at the same point where the hot fluid is entering, almost there. That means the length, if you consider the length between these two fluids, hot and cold fluid entry and exits, so for that length L, you can see the temperature variation for parallel flow and counterflow different. And the third case, according to flow arrangement, is cross flow heat exchanger. In this case, the two fluids for which heat exchange takes place, they flow at right angles to each other. So this may be further classified as unmixed flow and mixed flow depending on the type of configuration. One such configuration is this, wherein one fluid is mixed. You can see the gas in the sketch, the gas is mixed. There is no separate passage for gas flow. Whereas there is another fluid which is completely unmixed. They are separated out. As you can see, that flows through different pipes given, and there is no chance of mixing between the pipes there. So this case, it is cross flow heat exchanger, one fluid mixed and another fluid unmixed. And we can provide two separate channels for the fluids to flow through, and in such case they are not free to move in transverse directions, and this arrangement is called as unmixed type, that is both the fluids unmixed. You can see they cannot move in transverse direction. Gas flow, they are moving at right angles to each other. Gas flow is inside, is in between the gap between the plates, and whereas the cooling fluid, there is another fluid which is flowing through the pipes. Classification of heat exchangers according to constructional features. First among them is tubular type heat exchangers. Since we have already got familiar with parallel flow and counterflow, those are basically tubular type heat exchangers wherein two pipes are used, and you can see there is a central pipe. In this sketch, cold fluid is going in, and when it is coming out, it is warmed out, and there can be a hot fluid supply at one end, and this is actually a parallel fluid exchanger which comes under tubular type, and when the hot fluid is going out, it has become cooled down, and this case employs two different pipes, so we call it as tubular type heat exchanger, because of which it's also called as tube in tube or concentric tube or double pipe heat exchanger. So we can see one fluid flows inside the pipe and the other fluid flows inside the annular space, flows in the annular space between the two pipes. Shell and tube heat exchangers are widely used in engineering applications, and you can see in the CAD model of this shell and tube heat exchanger, there are many number of pipes arranged in parallel, and they are completely cased inside a shell, and you can see the baffle plates which are used to facilitate the flow of one fluid which are flowing over this. Basically these are called as surface condensers. Surface condensers are those, there will be an heat exchange between two fluids separated by a pipe surface, and these are more commonly used in heating, cooling, condensation and evaporation applications. That means wherever you see this heat exchanger to be taken place in large amount or large rate of heat transfer, then you will employ a shell and tube heat exchanger. As you can make out, there is a shell in which there will be a large number of parallel tubes of small pipes housing in it, and the heat transfer takes place between one fluid which is flowing through the tubes and the other fluid outside the tubes through the shell. Okay, there is one fluid which is flowing through the tubes, and the another fluid is flowing over the tubes inside the shell. And the baffles are those plates what you can see. They are used to create the turbulence in order to enhance heat transfer rate and to keep the uniform spacing between the tubes so as to increase the rate of heat transfer. There are different types of shell and tube heat exchangers, depending on the number of passes of the tubes and the number of passes of the shells. That is, the tube, the fluid which flows through the pass may take a turn, and also the fluid which passes through the shell may take some turns. So, the first one is a very simple example of one tube pass and one shell pass, where the fluid which is flowing through the tube takes one pass only. The left side is the inlet to the leftmost point, if you can see left top cold fluid inlet, that is flowing through the pipes, parallel tubing of the pipes there, and hot fluid will be entering the shell. It is entering the shell. That is, the hot fluid exchanges the heat from the cold fluid through the surfaces of the tubes, and as it flows, you can see the use of cross baffles. These cross baffles are used to allow or direct the flow of hot fluid or a fluid which is flowing in the shell so as to take some diversions, so that long residence time is available, so that there will be maximum heat recovery or heat exchange between the two fluids. And as you can see, there will be separate outlets for hot and cold fluids for this shell and tube heat exchanger. This is a case of one tube pass and one shell pass shell and tube heat exchanger. But we can have two tube pass and one shell pass also, wherein fluid which is flowing through the shall take only one pass from the left end to the right end, as you can see from the sketch, whereas the fluid which is flowing through the tubes can take a U-turn here in this case, that is a second turn. You can see the right bottommost point fluid inlet temperature inlet, and from that the fluid is flowing through the tubes, and when it is moved to the left extreme point, and provision is made for the movement of these fluid into a second pass, the second row of tubes parallel arrangement, so that the fluid comes out in the fluid outlet one for the fluid. So in this case, you can make out one shell pass and two tube pass shell and tube heat exchanger, and likewise you can have two shell pass and two tube pass, or two shell pass, four tube pass likewise, so that all these arrangements are made to enhance the rate of heat transfer. And there can be plate type heat exchanger, wherein there will be rectangular flat plates which are usually spaced from 1.5 to 2.5 centimeters apart, so that there will be a passage for flow of hot and cold fluids. As you can make out from the sketch, there will be gas flow through the gap between two plates, and in between this alternate gaps they can see the flow of another fluid. So this possibility calls for most expensive method, and both in terms of initial cost and also maintenance cost, because if there are any sediments or fouling occur inside this, it is very hard to maintain, and usually the initial cost is also high. But because of that reason, they are not used always, but wherever there is space requirement, then when you want to exchange the heat with minimum space available, then in such cases this plate type heat exchangers are used. Compact heat exchangers are a special class of heat exchangers wherein the heat transfer surface area available is very high. There is a term related to that, the rate of heat transfer, the ratio of heat transfer surface area available to the volume of the heat exchanger. Look at that. Surface area density is the ratio of heat transfer surface area to the volume. So, for a good heat exchanger, according to Newton's law of cooling, Q is directly proportional to area, surface area available, and the temperature difference. And because of that reason, usually when there is a limitation to other parameters, we may employ fins. But in heat exchangers, if we can have the maximum area to the volume, such heat exchangers are called as compact heat exchangers. There is a criterion for that. A heat exchanger with surface area density greater than 700 square meter per unit volume, that is 1 meter cube of heat exchangers, then they are called as compact heat exchangers. There are many different configurations in order to increase the area. You can see the plate arrangement in the first case A, and the circular fins and different types of fins in C and D, so that the area is enhanced for the same heat exchanger. And it is to be known that human lungs are considered as the most compact heat and mass exchanger with a surface area density greater than 20,000 square meter per meter cube. Based on heat transfer process, we have direct type or direct contact type. The best example is cooling tower used in a power plant, and as you can see, these are tall structures, and the left hand side of which is shown with the actual working principle, whereas the right hand side is the actual cooling tower. And what we can see from the left hand side is the hot water which is to be cooled is sprayed down through different nozzles, and when it is being sprayed down and the water when it is falling down, there is a passage for allowing air through the cooling tower, and this cool air, either using a fan, induced rot or forced rot, that will take away the heat from the hot water, and as the air comes out of the cooling tower, it will be warm moist, and the condensed water molecules will be settled down in the water basin or water tanks. And remember, in this kind, there will be an there will be a direct contact between the two surfaces, two liquids which are immiscible, which cannot be mixed. And in this case of cooling tower, there air can carry some of the moisture content, but still it is used. So in case of a cooling tower, usually one of the fluids is sprayed from through the other. There are many useful applications of this direct contact type, as you can see in case of a cooling tower, or in case of jet condensers, or also in re-superheaters and open feed waters, feed water heaters, and also the scrubbers. And these are all different components of a power plant. Uh, we will have a different course on power plant engineering or energy engineering, wherein all these components or accessories of power plant will be detailed, and they will be studied in detail. Recuperators are those heat exchanger where there is a direct heat transfer from there is a heat transfer between two fluids which are separated by a surface. As you can see, this is the simplest example of this. There is a wall separating between the two fluids in this case, and this kind of heat exchangers finds their application in almost all the fields of engineering. There are quite a big few list here. In case of a waste heat recovery heat exchanger or recuperator, where there is an exchange of heat between the waste gases and air, and the arrangement types can be different. The first one is different from the second one, where it is the second one is a convective evaporator, and metallic radiation recuperator and convective radiator. The mode of, depending on the mode of heat transfer, these are all classified, but the basic idea is to recover or to recuperate the heat from one of the fluid. So there will be a transfer of heat, so it's also called as transfer type heat exchanger. Regenerators or storage type heat exchangers are types of heat exchangers based on heat transfer process. In this kind, this hot and cold fluid does not flow on the same surface simultaneously, but alternatively they flow on the same surface. When this hot fluid flows in an interval of time, it gives its latent heat to the surface, and then this surface will store it in the form of an increase in the internal energy, and that will be released when a cold air or cold fluid flows over it. And in this case, generally there will be a heating period and a cooling period. For example, if you take an example of regenerative air preheater, the heat of flue gases flowing through the heat exchanger is transferred first to the packing of the heater, the packing which takes the heat, which stores the heat, and that heat is accumulated in the packing, and then the hot gases are cooled during its flow to its lowest temperature before they exhausted to the atmosphere. But in the cooling period, through the same packing material, there is cold air pass through the same packing, so that the accumulated heat is taken away by the colder air, and when it comes out, the air becomes warmer, and this hot air can be used for other applications. So there can be an alternate heating and cooling periods in such cases, and we have got improved models of this stationary types and rotary types. Rotary types can have continuous transfer of heat, where we have got one section of heating packing and another cooling packing, but we are not completely discussing it now. Based on physical states of fluids, that is, depending on whether fluid is being evaporated or fluid is being condensed during the heat transfer, we have condenser and evaporator. Condenser, we know that we have temperature enthalpy curve for pure substance formation, wherein you supply heat and study 1 kg of water under different states, starting from its 0 degree Celsius till its superheated conditions. In that, it's very clear that boiling temperature or saturation temperature of a fluid at constant temperature during its phase change remains constant. That means whether liquid saturated water converts from its condition to dry vapor state, or whether the dry vapors gets converted back into liquid vapor state, this takes place at constant temperature, that is saturation temperature. And in condenser, the hot fluid, which is nothing but the steam, remains at constant temperature, and the cold fluid, which is generally the coolant used to reduce the temperature of the hot fluid, gradually the temperature of which gradually increase from its inlet to its outlet, and the steam enters the condenser, and when it comes out, it will be in liquid form. It's also called as condensate. And you can see the temperature variation for the same. The temperature of the hot fluid in case of condenser remains same along its direction or along its length of the heat exchanger, whereas temperature of the coolant increases from its inlet to outlet, that you can see from the sketch. This is opposite for an evaporator. Let us see that. For an evaporator, the temperature of the cold fluid remains constant, whereas the hot fluid temperature gradually decrease from inlet to outlet. Usually in case of evaporator, there will be an entry of liquid liquid form, and when it comes out, so the way you can see the vapors of those liquids, and there will be a heat supply from a hot fluid, and that hot fluid loses the heat during the heat transfer because it loses the heat, and there will be continuous change of phase from liquid to vapor in the evaporator, because of which that should take place at constant temperature or saturation temperature. So temperature of the cold fluid remains same throughout the heat exchanger in case of an evaporator. That can be just cross checked here. Temperature variation for both the condenser and evaporators are shown here. Temperature of hot fluid remains constant in condenser. Temperature of cold fluid remains constant in evaporator. Thank you.